In this video, we're going to look at similarity and diagonalizations of matrices. So what does it mean to be similar? Well, we've talked about row equivalent matrices. They're not equal, but they're row equivalent. Those matrices are similar. So suppose A and B are two square matrices of size n, then A and B are similar if there exists a non-singular matrix of size n, and we're going to call it S, such that A is equal to S inverse of B and then multiplied by S. So let's look at A. Here's my example. We have this matrix A, and I want to know if B is similar to A, given that this is going to be my similar to S. This is going to be my S, and this is going to be my D. And it should be, let's fix this, if D is similar to A. So the first thing we're going to do is find the inverse of P. And if you remember that the inverse of a 2 by 2 is 1 over A multiplied by D subtracted by B multiplied by C, where the D and A switch position and B and C switch signs. And this is going to be the inverse. We'll call it, call this one B, where, of course, B was equal to the A, B, C, and D. So there is how we found this inverse of this 2 by 2. Now let's do the matrix multiplication. I'm going to take my inverse, or actually I'm going to do, and the order in itself doesn't matter. So up here I said it had to be S inverse multiplied by B multiplied by S. I can also do P multiplied by D and then P inverse. That's okay. The order, if you have the inverse first or the inverse last, it doesn't matter. So I'm going to do this multiplication. Here is my P, here is my D, and here is my P inverse. When I multiply all these, I get back to where I started, which is A. So that means that D, this should be D, is similar to A. Let's take a look at another example. Here is how I'm going to define B. Here is how I'm going to define S. And I want to find a matrix similar to B. Now, in the first example, we were checking to see if the two matrices were similar, giving this P matrix. And in this case, I'm given the B matrix and my S matrix, and I want to see if I can find a matrix that is similar by the definition. So, of course, I'm going to find the inverse, regular ways of finding the inverse. For this is the inverse of S. Here's my B matrix. And here is my S matrix. And when I do this matrix multiplication, I get this matrix, which is actually kind of a nice matrix. It got diagonals here of -1, 3, and -1. That's a really nice, similar matrix to this matrix here. So let's go on to some theorems. And so my first theorem, and of course all the theorems are in your book for your viewing pleasure. Suppose A, B, and C are square matrices of size n, then A is similar to itself. If A is similar to B, then B is similar to A. We have symmetry. If A is similar to B and B is similar to C, then A is similar to C. So that's kind of nice. The other one we have is suppose A and B are similar matrices, then the characteristic polynomials of A and B are equal, and that the characteristic polynomial of A of x is equal to the characteristic polynomial of B of x. And you can use lambdas there if you want instead of the x's. We know that in our previous video we did that. We used lambdas instead of x's, but there's our characteristic polynomial. So what that tells us is that similar matrices, not only do they have the same set of eigenvalues, the algebraic multiplicities of these eigenvalues will also be the same. So if they are similar matrices, they'll have the same eigenvalues and their multiplicities will be the same. That's not true the other way. And what I mean by that is that just because you have two matrices that have the same eigenvalues and the same algebraic multiplicity, that does not necessarily mean that the matrices are similar. So that's what I mean. The converse is not true. So then let's define what a diagonal matrix is. We hadn't really formally defined what a diagonal matrix is, but now we will. Suppose A is a square matrix, then A is a diagonal matrix if I have zeros in every position except for down the diagonal. The A11, the A22, the A33, etc. So that's what it means to be a diagonal matrix. We've now formally defined it. And we say that a matrix is diagonal diagonalizable if it is a square matrix and if A is similar to a diagonal matrix. So cool. How do we find this magic matrix that allows us to diagonalize a matrix? Well, let's have one more theorem. Here's the next theorem, then we're going to go through a process. I'm going to show you how to do this. Suppose A is a square matrix of size n, then A is diagonalizable if and only if there exists a linearly independent set S that contains n eigenvectors of A. So, we're going to find those matrices. We're going to find the matrix P, and then we're going to find the matrix D to diagonalize A. We go back to this. This is what we learned in our last video. So the determinant of my A matrix minus lambda multiplied by my identity matrix of the same size gives me this. And this gives me my characteristic polynomial, which factors. So we did that in our last video, so no surprises there. So we get these eigenvalues from our characteristic polynomial of 1 and 2. We start out with our first one, and what we're going to do is we're going to find the eigenvector that's associated with this eigenvalue, just like we did in our last video. So we take, of course, our A minus 1, that's our 1 is right there, so that's our lambda, and lambda was 1. So it is our A matrix subtracted my identity matrix times our lambda, which is 1, which is this, and it is then, of course, augmented by a homogeneous system, so this is the augmented matrix. And then we end up with a reduced row echelon form, which gives us this, which then gives us our eigenvector. And of course, our eigenvector is the null space of this. So there's my eigenvector. We do the same thing for lambda 2. We solve the system. A minus 2 times my identity matrix, of course, is going to be an augmented homogeneous system. So we're going to augment that on. This is augmented, this is augmented. And we get our second eigenvector. Our second eigenvector is this. Now, let's define what P is. P, the one that I'm going to do the inverting on, is going to be, by my theorem, that it's as long as these are linearly independent, which of course are my eigenvectors, U1 and U2. This comes from lambda 1 and lambda 2 is here. Here is my U1 and here's my U2. I'm going to define my D matrix, as being the lambdas in those positions, lambda 1, lambda 2. Along that diagonal, if I have something larger than a 2 by 2, I'd have a third one to be lambda 1, 2, and 3 in the diagonal. So there's my D matrix. So now I found my P matrix, I found my D matrix. And then I'm going to go ahead and check. So the way I'm going to do it is I'm going to check by doing P multiplied by D multiplied by P inverse, finding our regular way of finding the inverse matrix. And I end up with A. So let me recap what we did. To find this P matrix, the first thing we did was we found the determinant of A minus lambda I sub n. That was the first thing we did. The second thing we did was we found, this is just kind of a recap, we found the solutions, or we found the factors of the characteristic polynomial. Then the third thing we did, let me just go over here. The third thing that we did is that we then went back to the A minus our lambda 1 in, or whatever our lambda was. So I'll call it lambda, I'll call it 1. Multiplied by my eigenvector is going to be 0. So I solved the homogeneous system of A minus lambda I sub n to find my eigenvectors. And the way we did that, that was the null space. To remember the null space, it was the null space of A minus alpha, or lambda 1 I of n. So then once I found my null space, and I had to go through this process, however many lambdas I have, So you're going to go through this process, this part, as many times as you have lambdas. Okay? And then once I did that, then I know my S or P or whatever it's going to be is going to be those eigenvectors. So x sub 1, x sub 2, however many you have for the eigenvectors. Or if you prefer, you can use U's. It doesn't matter. You can use x bars or U's. It doesn't matter. And my B matrix, or D if you like, is going to be the lambdas in the diagonal. So lambda 1, lambda 2, all the way down to however many lambdas you have. We'll call it lambda, I don't want to use n, let's use lambda, what do I want to use? M? Lambda m. And of course there's zeros everywhere else. So zeros down and zeros across. And so that's where my B matrix, if you will, or D if you want to call it D, that's how I find those two matrices. Okay. So now we want to find a 2 by 2 matrix A that has these given eigenvalues and these corresponding eigenvectors. So what they're doing is these are the columns to the P or S, if you will, and my D or B, if you will, is going to be those lambdas and those diagonals. And I'm going to be able to take these two matrices and multiply them together with the inverse and find the A matrix that is going to be given those eigenvectors and those eigenvalues. So I end up with P, D, P inverse. This would be similar to saying A, S inverse, B, S. Depends on how you want to label it, but the gist is the same. So here's my P matrix. Here is my D, or B if you will, and here's my inverse. And so this is my A matrix. And I can check it, right? I can check it by doing my A matrix multiplied by my first eigenvector. And of course, I get the eigenvector with a multiplier of lambda of equal to -1. So that falls from before. We had the lambda of -1. And then, of course, here's my second check, and it is my A matrix multiplied by this eigenvector, which ends up giving me 6 and 4, which is a multiple of my eigenvector. So my lambda again, which I had up above, was 2. So these do check out. So let's move on to the next theorem. The next theorem says, diagonalized matrices have full eigenspaces. Suppose A is a square matrix, then A is diagonalizable if and only if the gamma sub A of lambda and the alpha sub A of lambda. Remember, the gamma sub A of lambda is the geometric multiplicity or the dimension of the eigenspace, and the lambda, of course, with the algebraic multiplicity for the eigenspace or the eigenvalues. So for every eigenvalue lambda of A. The next one says, suppose A is a square matrix of size n with n distinct eigenvalues. Then A is diagonalizable. So, if possible, diagonalize this matrix. So the first thing I do, as before, is I go back to the determinant of A minus lambda of this, because it's a 3 by 3 matrix, it is going to be lambda multiplied by that identity matrix, size 3, which ends up gives me this, which factors. So what I have is I have lambda being 0, and I have lambda is equal to -1. It has a multiplicity of 2. Starting with lambda is equal to 0, we're going to solve this system, which means that, of course, when we solve the system and we augment on that matrix, this is what I'm going to get. I'm going to get this, and go ahead and say that's an augmented, show it's augmented. Do the row reduced echelon form, and I have one free variable, and that is in this place. It's the only column without a pivot. And so the null space, or the eigenvector, is associated with this lambda is equal to 0, is 1, -1, and 0. And this is now why we spent so much time on null spaces. Let's go on to the next part. We have the lambda sub 2 is equal to -1. Then the augmented matrix, of course, that we have is this. And in this case, I have two free variables. I have a pivot in my first column, and then these, of course, are my free variables. So that gives me, using my null space, it gives me this. So my null space gives me this. And the reason the 2's are here is because I don't want to mess with having fractions. So when I do my null space and I write my variables, this would have normally have been a 1 and a -1/2 and then 0, but of course we don't like to really work with fractions or decimals, and that's how come this is a -2, is because I multiplied that vector by 2, and so I get that value. Actually, it would have been, my apologies, it would have been 1 here, 1/2 here, and -1 here, and then 0, and then I multiplied it by 2, so that's why there's a 2 there. All right, so I have an eigenspace that has a dimension of 2, right? Because it has a multiplicity of 2. The basis tells me that I have to have 2 vectors, and I do. Because the multiplicity is 2 on this eigenvector, I should end up with this eigenvalue has a multiplicity of 2. I should end up with 2 eigenvectors, and I do. And so here we are. This is going to be a linearly independent set. There are 3 vectors and 3 entries, which means we are having a basis in R3. They are linearly independent, and that tells me my D matrix is, these are my D matrix, these are my eigenvalues, 0, -1, and 1. And here's my P matrix. It is built by my eigenvectors. Again, these are my eigenvectors. This eigenvector was associated with lambda 1, which is equal to 0. That's why there's a 0 there. This and these two were lambda sub 2, which has equal to -1. And so those where the -1s are coming from. And of course, here are those vectors that I associated with that. So then, the number of the eigenvalues along the diagonal correspond, of course, to the eigenvectors. And we go ahead and do a quick computation. And we end up with PD and AP give me the same value. And the reason we did that is because if I have A is equal to P, D, P inverse, then if I multiply P on this side, I have to multiply P on this side, which is why I should have AP is equal to, and that should be D. That should be D. Let me change that to D. This is D. Has to be P times D. So that's because of the order in which you multiply matrices matters. So there we have it. Now, let's see if we can diagonalize this one. So again, we go back to this, and I end up with this characteristic polynomial. Lambda 1 is -2 with a multiplicity of 2. Lambda sub 2 is equal to 2 with a multiplicity of 1. When I go ahead and do the A minus the lambda 1 multiplied by I and augment it to make that homogeneous system, I end up with this. Now, it only has one free variable, and that's this one, right? Because you're going to get a pivot here, and you're going to get a pivot here. But I should have, because a multiplicity of that is equal to 2 on this, the multiplicity is equal to 2, I should have gotten 2 bases. Because I didn't end up with not two bases, but 2 vectors, eigenvectors within my basis. And that didn't happen. Because that didn't happen by my previous theorem, then I know that this matrix A is not diagonalizable. Because my previous theorem says this multiplicity has to match the number of eigenvectors for that lambda for the matrix to be diagonalizable. And it didn't, so it's not. You can't diagonalize A. So that's it. That's it for this section.